So let's move on to section 1.3, the cylindrical and spherical coordinate systems. So last week I already discussed about the rectangular coordinate system, which is also referred to as the Cartesian coordinate system. And in the Cartesian coordinate system, we know that a coordinate system requires 3 reference directions. For the rectangular coordinate system example, you need X, Y, and Z directions. And one of the property about the 3 directions is they are orthogonal to each other. They are perpendicular to each other. And the order, the X, Y, and Z order follows the so-called right-hand rule. That is, if you do the cross product among the reference direction, X cross Y will end up with the Z direction. On the other hand, if you do the cross product inversely, that is, Y cross X, you will end up with negative Z direction. And one of the important difference between Cartesian coordinate system with the other coordinate systems are the uniformity. That is, the reference direction orientations are the same everywhere in the Cartesian coordinate system, and they may not be the same in cylindrical and spherical coordinate system. So now let's begin with the introduction for the cylindrical coordinate system. And for the cylindrical coordinate system, the 3 reference directions are known as R, phi, and Z. And it's pretty much, it's quite similar to the so-called polar coordinate system. Have you ever heard of that? Well, I bet you already know that the polar coordinate system is so-called 极坐标 system. It's a 2-dimensional coordinate system. So in the polar coordinate system, you have one is R and 5. R is the distance from the origin to your observation point. And phi is the angle between the line from the origin to your observation point and the positive X direction. The polar coordinate system is often used to describe points on the complex plane. So to think of this, you know that the x-axis what is the direction of AR, and what is the direction of A phi? Well, this is not a trivial question because this is related to the definition of the reference direction. The orientation, the direction of the reference direction is always pointing toward the greater value of that parameter, of that variable. Okay, so for this point, the AR direction is the direction for larger and larger R. So it's pointing towards this direction, okay? So AR direction is pointing outward. What is the A phi direction? Note that, what is the phi angle at this point? It's close to 0 degree, right? 1 or 2 degree, something like that. So this is somewhere around 45 degrees. So what is the A phi direction? This way or this way? Which one? Well, as I already mentioned, the direction of the reference direction is toward the larger value of that variable. So that will be this direction, A5 direction. Okay, so keep this in mind because in the following introduction about the spherical coordinate system, this rule follows as well. Okay, so A5 direction is pointing counterclockwise, 逆时针方向 counterclockwise. All right, so okay, so if this is polar coordinate system, if we transform it, expand it into the cylindrical coordinate system, what is the z direction? What is the z direction? How do you find the z direction from R and phi? Because we know that the order of cylindrical CI system is R, phi, then z. So AR cross A phi will end up with the AZ direction. So according to the plot, well, how can you do that? How can you find that? AR cross A phi. So the AZ direction is in this way. Okay? So it's pointing out of the blackboard is the positive z. Okay? And you can try that if you do the cross product of A phi cross AZ, you end up with AR direction. If you do the cross product of AZ cross AR, you will get A phi direction, right? And the second thing on the slide is what is the geometry of fixing the parameter as a constant value. So if you fix z as a constant value, say z equals to 1, well, what would it look like? If z is set as 1, you will end up with a horizontal plane, right, for any arbitrary value of r and phi. And if you set r as a constant value, what would you get? If r is a constant, say r equals to 2, then you will end up with a cylinder extending all the way up to infinity, all the way down to negative infinity. It's a cylinder of r equals to 2. Okay, so if r is a constant, you will have a cylindrical surface. So what if phi is set up as a constant value? So if phi is set as 90 degrees, then what would you get? You will get an, infinite plane expanding from r equals to 0 all the way up to infinity, but not a whole infinite plane. It will be a half an infinite plane. It's sounds kind of strange. So again, so if you fix phi as a constant value, you will get a planar surface vertically, but expanding all the way from the origin axis to the infinity. So what is the dynamic range of z? What is the legit variant range of z? So what is the possible value for z? That will be from minus infinity to infinity. Okay? So how about r? What is the legit value for r? Well, r is the distance of your observation point to the origin axis. This is some difference with respect to the spherical coordinate system. For cylindrical coordinate system, when we say the origin for r or phi, or for r is the is actually the z-axis. It's not a point. It's a line, aligning with the z-axis. So r is the distance from the observation point to the z-axis, the shortest distance to the z-axis. So it's not a point. It's not a line to the origin. It's a line to the z-axis. So the variable range for r is 0 to infinity. Okay? And then how about phi? All right, by definition, phi is, the variable range for phi is 0 to 2 pi, or 0 degree to 360 degree. Okay? And what is the direction? What is the direction for phi equals to 0? Phi equals to 0 is aligned with the AX axis. So this is the axis, Y, and Z. So phi is starting from, phi equals to 0 degrees starting from x-axis, positive x-axis, and going up to the positive y direction, and the negative x direction, the negative z direction. Okay? So here are some basics about the cylindrical coordinate system. The next thing is we shall move on to the definition for differential length, differential surface, and differential volume. However, before we go to those differentials, what is the significance of the delta R? Oh, sorry, let me put it this way. The R, okay? Well, that's a small distance, a small difference in R. Okay? A very small change in the R direction. The phi is a small change in the phi direction. The z is a small change in the z direction. However, there is some distinct difference between the three. What it is? The z is a small difference in the z direction, but it also refers to a short distance in the z direction, right? The r is a difference in the r direction, and it's also a distance in the r direction. How about the phi? The phi is a small difference in the phi direction in terms of angle, in terms of degree. The phi itself is not a distance. The phi itself is not a distance. For example, if this is a record, 你说讲中文可能你都没有听过唱片是什么了嘛，对不对？看过吧，至少看过吧，流行文化总看过我看过吧，知道唱片嘛，黑胶唱片嘛，OK， 可能你家里没有真的听过但总看过吧，一些老音乐，我说黑胶唱片的质感音质最好了，OK 之类的。Alright, suppose that you have a disc player, okay? And of course you have a rotating disc. And well, I forgot the exact spec for record player. It usually comes with some specs say 25 RPM, 45 RPM. What does that mean? 45 RPM means 45 revolutions per minute. So if you rotate it about 1.3 seconds a revolution. So within 1 minute, it will rotate 45 turns. And what is the moving speed on the disk if you are a small ant? 所以假如你是小蚂蚁啊，在是上面好了，你移动的速度会怎样？ If your position is close to the origin, the moving speed of you will be a little bit slower than another ant placed on the outside of the disk, right? So even though both of the two ants moves in the same amount of RPM, revolution per minute, the actual moving velocity is different. The distance they traveled are different. So, how to determine the velocity, the speed of the two ends? That will be what? The amount of angle change times the distance from the end to the origin. To the central axis of rotation. So you need times the distance r of your observation points to get the change in distance in the phi direction. All right? So r d phi becomes meaningful when it comes to the description about the distance in the change of distance in the phi direction. Okay? So, well, most of the things in this slide has already been discussed. Okay, so you fix x, r, phi, z as constant value, you end up with a cylindrical surface, a plane for a constant phi, a plane, horizontal plane for constant z. The variant range between for r is from 0 to infinity, phi for 0 to 2 pi, and z is minus infinity to infinity. If you fix two parameters, say r and phi, you will end up a line on the z-axis. So you fix two surfaces. If you fix the description for two surfaces, we will end up with a line in the three-dimensional space. And here is the so-called direction. One important thing that I mentioned at the beginning of the lecture is the uniformity. The uniformity is holds for the z direction for cylindrical coordinate system, but it's not the same for r and phi. So let's make a practice. Say if my microphone is pointing to the positive z direction, and this is the origin axis of our coordinate system, and you try to describe yourself in a cylindrical surface. So, okay. So if I'm standing right there, right here, okay. So what is the r direction of mine? This way, right? Pointing outward. How about you? So what is your AR direction? By using this as the reference, what is your AR direction? What is your AR direction? Not toward me. You need to point in toward a value of greater r. So that is the direction moving away from the axis. All right? Okay, so it's kind of arrowheads pointing outwards for your r direction. And your r direction, AR direction is not the same as your AR direction. It's not the same as my AR direction. Okay? How about the A phi direction? So I'm standing here. So my A phi direction will be this way. So how about yours? All right. Okay. So you need to refer to the z-axis and try to find out the A phi direction of yours. And it's not the same with other classmate or other position in this classroom. All right, so every place in this classroom do not have the same AR direction and A5 direction. But we all have the same AZ direction, that is on the top of our head. Okay? So that is the reference direction for cylindrical coordinate system. Nevertheless, the so-called mutually orthogonal unit vectors, or the perpendicular between the reference direction, still holds for any points in this three-dimensional space defined in the cylindrical coordinate system. That is, AR cross A5 will end up with AZ direction. A5 cross AZ will become A5 direction. Okay? What next? Okay, so that's the, well, AR cross A5 is AZ, huh? A5 cross AZ is AR. AZ cross A5 is minus AR, okay? And here's an example. So, is this a cubical volume? Is that a cube? Of course not. This place, this space, this volume is defined in terms small difference in the z direction, small difference in the r direction, and small difference in the phi direction. So these three short lenses, these three short distance, expand a small volume in the cylindrical coordinate system. It's not a cube as we find in the Cartesian coordinate system. Nevertheless, if the difference, say dr, d phi, dz, are very small, they shall approximate. 什么是 approximate? 趋近, They shall approximate a cubic volume, as you can see from the plot, right? So if it's really small, well, then it's pretty much like a small cube. So for calculus, when you talk about differential equation or a small difference in the space, well, even though they are not, the cylindrical coordinate system is not really the same as the Cartesian coordinate system. But when the distance or the change is small, they still approximate as a cube. And what next? Okay, so next is the description for differential length. So I believe you still remember the definition for differential length in the rectangular coordinate system. So dl, a differential length, equals to what? dx ax plus dy ay plus dz az. So they are corresponding to small difference in the x and y and z direction. So how about the differential length in cylindrical coordinate system? There will be dr, small change in the r direction, ar plus d phi, a phi plus dz az. Is that right? Well, no, because I already mentioned r dr is a distance, dz is a distance, d phi is a difference in angles, but not a distance. How to make it a distance? Well, you need to try another variable r in this description. Well, r is a variable. You say r is a variable. It can be different places. Then It can be a different, well, we are talking about the L, a short distance, a very localized distance. This is, the distance is so short, so small, that R is nearly a constant value. So this is okay to write in this way, all right? All right, so we have the definition for differential length in the cylindrical coordinate system. Next are the differential surface vectors in the cylindrical coordinate system. And because differential surface is a small piece of area, and it is not a closed surface, so the direction of the small surface has actually two normal vectors, one pointing upward, the other pointing downward. So all the description here, they have positive and negative sign. So this one is a space, an area spanned by AZ and AR. So the surface described by this small area on the ZR plane will be dz cross dr AR. So that will be dr, dz. They describe the size of the surface times a phi, right? Az cross AR ends up with a phi. Yeah, correct. All right. So you can do the same for the other two planes. This one is a surface is spanned on the phi z plane. However, you know that the phi itself is not a differential length, so you need to get a modification r here to correctly represent a surface area in the phi z plane. And so is the case for the r phi plane. So you have r, d phi, dr in the az direction. And the next is the differential volume. So differential length is a vector, differential surface is a vector. How about differential volume? Differential volume is a scalar, all right? Length is a vector, surface is a vector, volume is not a vector, it's a scalar, all right? And it's the product of the three differential lengths on the reference direction, so that will be dr times dz times r d phi. So the differential volume described in the cylindrical surface, cylindrical coordinate system requires a modification term r in its differential volume. Okay? So you are recommended to go over the slides to get acquainted with the basic definition for cylindrical coordinate system. Next is the spherical coordinate system. From the perspective of the study of electromagnetic wave, spherical coordinate system is of course more important. Because what? Well, because the source of electromagnetic wave is usually a point source. So all the electromagnetic wave originating from a source of limited sizes. Even though for a gigantic source like the sun, which is enormous from the human perspective. Nevertheless, as you move away or you stand away from the location of sun, it turns out to be a small point in the universe. So eventually, even though on the surface of Earth, the sunlight, the intensity of sunlight is nearly a constant at the Earth's surface. As you move away from the sun, it becomes as more and more like a small dot in the sky as you view all the other sun in the galaxy, in the universe, right? So it's kind of nature to describe the propagation of electromagnetic wave in terms of spherical coordinate systems. It can give you more precise description. However, in the study or in the problem-solving procedure of electromagnetic problems, we usually apply approximations so that the solution can be simplified. So sometimes we can use rectangular coordinate systems to describe the problem so that the solution can be a little bit easier. However, we will still need to learn the basics about the spherical coordinate system. So first thing first, what are the three reference directions of spherical coordinate system? 球坐标系统的三个向量是哪三个 ？R, theta, and phi. R is the distance from the observation point to observation point to the origin, which is a point. So this is the origin. O is a point, not a line, as we have seen in the cylindrical coordinate system. So this is point P. So the distance from the origin to the observation point is the value of R. So what is the variable range for R? R 的变动范围是从哪里到哪里 ？0 to infinity, right? From 0 to infinity. So it's varying from 0 to infinity. Next is the theta. Theta is a length or an angle. Theta is an angle. Okay? So which direction is theta equals to 0? So theta angle begins from positive z direction. Okay? So it's starting from the top of your head, AZ direction. So theta is a description between the angle difference from the z direction to your observation point. So what is the variable range for theta? 0 degree, 45 degree, 90 degree, 135, 180. And, well, so the variable range for theta is 0 to, let's describe it more precise, 0 to pi, okay? Or 0 to 180. So that is the variable range for theta. Next is phi. Well, its definition is similar. I cannot say the same as the phi in the in the cylindrical coordinate system. They are similar, but not the same. It's the angle between the x-axis and the projection of R on the xy plane, and the angle between the projection and the AX direction is your phi angle. So this is not a direct angle difference between R, the vector P, and AX. Is the angle between the projection of a vector P on the xy plane and AX. Okay, so you need to be careful about the definition of phi. So what is the variable range for phi? 0 to 2 pi, right? So it's similar to the definition in cylindrical direction. So let me see. Okay, so what is the for this figure? What is the implication of this figure? This figure says if you fix R as a constant value, what would you get? What kind of geometry would you get? If you have a geometry made of a constant R, you'll get a sphere. 一颗球嘛, a sphere. What is the geometry if you fix theta as a constant? Theta 是定值的话，你会拿到什么？ We end up with a cone. What is a cone? When you buy the ice cream from the family, right? So cone, you end up with a cone, right? Of course, you have a cone pointing upward or pointing downward. What is the geometry if you fix phi as a constant number? You get a half plane. Expanding to the infinite, okay? So a plane, a cone, and a sphere. If you fix phi, theta, and R as a constant. So a point, any point in the spherical coordinate system can be described well, R, theta, phi can be used to define or to address any point in the space. Okay, so any point in the space can be specified from R, theta, and phi values, except 2 points. 求坐标系统有一点点盲点的，有2个盲点了哈。它在有2个地方上面的描述是比较尴尬的哈，你知道吗？哪里？ Well, so most of the points in the 3-dimensional space can be specified using R, theta, and phi value. However, if you are, say, on the surface of Earth, if you're standing just right on the North Pole, or just right on the South Pole, I mean in the Antarctica or the Antarctica continent, what is the R, theta, and phi value on the North Pole? R value specifies the distance from where you stand to the center of the Earth. Right? So R value is fine. How about the theta? Well, for the North Pole, is theta equals to 0 degree. No, that's okay. In the South Pole, theta value is 180 degree. How about the phi value? Well, so in the North Pole and the South Pole, you don't have a definite phi value. So that is probably the only 2 points that cannot be clearly specified in terms of r, theta, and phi. All the places in the universe can be addressed in terms of r and theta and phi values. All right? And well, next is the reference direction. We know that r, theta, phi is a set of reference direction in the spherical coordinate system, and they follows the sequence follows the right-hand rule. So AR cross A theta end up with A phi direction. A theta cross A phi will be AR. AR cross A phi is what? Negative A theta. So be careful about the sequence. And the reference direction are not uniform. So my AR direction, say this is the origin of the classroom, all right? So from your own perspective toward the origin, what is your AR direction? This way. Pointing outward, always pointing toward the larger value. So what is theta equal to z direction? So what is the direction of theta equals to z? Pointing upward, theta direction. However, from your own perspective, what is your A theta direction? What is the direction of mine in terms of A theta? Well, theta equals to 0 is over there. For me, it's 70 degrees, right? So the angle between z-axis and me is 70 degrees. However, the A theta direction is what? Is from 70 degrees goes to a larger value. So my A theta direction is towards this direction. AR, A theta, how about A phi? AR cross A theta, A phi. So that's my A phi direction. And my AR, A theta, A phi direction are not the same with your own. Okay? So they are not a set of the same value. So here this figure tries to describe the volume, the space between point P and point Q. Point P and Q are not in the same location, so they have some difference in R, some difference in theta, the theta. However, the theta is not a distance, it's a difference in angle. So the distance in this direction shall be r d theta. R d theta. Okay, so here comes the most complicated part. What about the difference in the phi direction? We know that for point P and point Q, the difference in the phi direction is d phi. However, the distance, the actual distance, difference distance in this direction will be r sine theta d phi. Okay, so be careful about that. R sine theta, what is the significance, or what is the significance of r sine theta? This is theta, right? The angle between observation point and z-axis. This is r sine theta. R sine theta is r, the projection of r on the z equals to 0 plane, the xy plane, the horizontal plane. So the distance in the r direction, the differential length in the r direction is dr. In the theta direction is r d theta. In the phi direction is r sine theta d phi. Okay? R sine theta d phi. And here are the definition for the three differential surfaces in theta phi plane, r theta r phi plane, and r theta plane. And for the description for the differential volume defined in the spherical coordinate system, you have the product of dr d theta d phi and two modification terms, that is r and r sine theta, which are used to address the distance in the theta direction and the distance in the phi direction. All right? So be careful about this. Okay, so to conclude our discussion today, so here's some practice. What is the distance if you're moving from latitude 23.5 degree to latitude 24.5 degree? What is the difference in terms of theta? The theta is actually 1 degree. The theta is actually 1 degree. So, what is the distance? Well, here's some clue. The radius of Earth is about 6,400 kilometers. And how to find this R value? That should be 6,400 degree times the theta, which is approximates to one degree in tangent. And one important mathematical property is that if the angle is really small, the tangent is just like itself. So actually you can do it as pi over 180. So it's about 101 kilometers. So if you're moving in the latitude, it's about 111 kilometers in terms of 1 degree. How about you move from 120 degree longitude on the equator? It's about 111 kilometers as well. However, if you're moving on the North Pole region, on this position, this distance will be much shorter. Okay, so, well, in the novel, traveling around the world in 80 days, it takes 80 days to travel around the world because you need to go around about 40,000 kilometers on the equator. However, for Santa Claus, it probably takes only 5 minutes to circling around his house to go around the world. So it takes about less than 5 minutes, right? So it depends on where are you stand